Welcome everyone. So this is our 1/20th live stream geometry. The 2023 IMO just happened very recently. So last session we did problem 2 on it, but this session we're going to do problems from the 2022 shortlist. So we have 3 people here with us now, and 2 of them were actually participants at the IMO. Well, at least 2. Drew, I'm not sure about if you were there. But if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so let's get to the first problem. So this is from the 2022 shortlist, which I believe they released the same day that they released the IMO problems. So let me maximize. So we have triangle ABC, and F is the altitude from A, and P is a point on that segment. Let me see if my altitude tool will work. Yes. So this should be F, and this should be P. Then we draw the line through P parallel to AC and AB, and we see where they meet BC. So these 2 lines. So yeah, I'll draw more points than just what it says to draw. So the line parallel to AC meets it at D, and the line parallel to AB meets it at E. Let me draw these points also, because then this is a parallelogram, which maybe would be useful. So then we draw the circles ABD and ACE. And so DA is equal to DX. So X is on ABD. So this is X. Let me hide this circle. No, not that circle. Let me hide this circle. So DA equals DX. So I'll draw this triangle. It's isosceles. And EA equals EY. So that's where it should intersect the circle ACE. So EA equals EY. All right. So we have 2 isosceles triangles coming from D and E. And we want to show that BC, X, and Y are cyclic. Now that doesn't look true, or maybe it does actually. Let's check it. So BC, X, and Y. Yes, that is true. All right. So P can be any point, which is kind of interesting. Any point on altitude. We have this parallelogram. Obviously, PED is similar to ABC. So what should we do from here?
Maybe trying to use the radical axis theorem or something, because all the points are on the circles.
Okay. So I wonder if AF passes through this point, maybe? Let's see. Looks like it. Let me move things around. Yeah, so maybe first we could show that these circles, we just need to show F lies on the radical axis of these 2 circles, right? And that would solve it. Or we could just show P lies on the radical axis, right? So that would be step 1, and then step 2 once we know that, then by the radical axis theorem, bx and cy should intersect on it. So yeah, we could try to solve this in 2 steps like that. So can we show either that P or F have the same power with respect to these circles? Let's see. So FV times FB, we could try to show that's FE times FC. And that looks like it should be, you should be able to do that with similar triangles, right? Because PDF is similar to ACF, and ABF is similar to PEF. So I think, yeah, using those, I think it shouldn't be hard to show that BF times FB is EF times FC. And so from there, that would mean that F lies on the radical axis, so that this is collinear. Okay, so that would be step 1. I left out a couple calculations there, but I don't think it's that hard, because just using the similar triangles, I think, is probably enough. Because DF over FC is PF over AF. So and EF over BF is also PF over AF. So I think just that would finish the calculation. So basically, we want to show that these are all collinear. We know that these are, and then that would solve the problem. Okay. So we could try to show J lies on the radical axis.
It looks like the reflection of A. Maybe I'm wrong, but
yeah, it looks like these are both. Yeah, it looks like the reflection of A.
and I think it sees it by angle chase. Yeah.
Wow. So this is not a very hard problem. Okay. So you just angle chase to show that J is the reflection. And once you've shown that, then I'm sure it's not hard to, since it's a reflection, it has to lie on this. So then you just use power of the point. So yeah, so it's a fairly easy problem. Okay. All right. So we have, let me write it out on paper and then I'll type it up. Like I find that's easier usually. So BF times FD is EF times FC times FP over AF, and then EF times FC is BF times. Okay, so here's what we have. So we have EF times FD is equal to, do this, to BF FC times FP over AF. And then we also have EF times FC and that implies A, F, and I are collinear. So I'll make this look a little better. step 1. And then after that, let dx and cy intersect at J. And then now we're going to show J is just a reflection of A over BC. So that should just be an angle chase, because angle JBD is angle XAD, which is angle DXA, which is angle DBA. So I'm just going to write that out on paper first. So JBA is XAD, which is AXD, which is ABD. So B, which is AXD, which is ABD, which is ABC. And then similarly, angle J, did I mean JBA or JBC? I meant JBC. JCB is equal to angle ACB, and that implies J is the reflection of A over BC, which implies AF and J are collinear. And that means that JB times JX equals JI times JA equals JY times JC. Or J, I think it's J, what is it? JI, yeah, JI times JA equals JY times JC. And that means that ECXY is cyclic. All right. So yeah, not too hard. So yeah, thanks. We will move on to the next problem. Yeah, the reflection finishes it off pretty easy. Let's see. So we have a cyclic quadrilateral ABCD, and QABP are collinear. So how are they collinear? Let's see. So I'm probably going to want to draw the whole line AB, not just a segment. So it's saying they're collinear so that AC is tangent to ADQ and BD is tangent to BCP. So let's think about this. AC is tangent to ADQ. How do we draw that? I guess we'd want to drop a perpendicular. So the center has to be, I guess we want to intersect that with the perpendicular bisector of AD, and that would be the center of the circle, I think. Let's check that that's actually correct. So I think this would be the center of it. So let's try this. Okay, so this would be point Q right here. It's Q. And now we want to draw P. So we do the perpendicular bisector of BC. And we want to see where that intersects the perpendicular from B to BD. So this. Okay. Is it this point? I think it is. And then we draw the circle, this circle. And no. We draw this circle, I think. And we see where it intersects AB. So it should intersect at P, I think. So BDS. Okay. All right, so let's get rid of a lot of unnecessary lines here. We don't need the whole line here. So AC is tangent to that one, and BD is tangent to that one. And yeah, we probably don't need these two. We could just keep the centers. We might as well. Whoops. And let's just connect these, and I think we have it. So M and N are the midpoints of PC and AD. This should be M. And this should be N. And we want to show that CD, the tangent to A and Q at A, and the tangent to BMP at B. So basically, if we draw these two circles, and we draw the tangents at A and B, we want to show that they meet on CD, which is kind of interesting. Let's just check that that's true. So that's one tangent. This is the other tangent, and it looks like they do. So let's draw. We don't know this point exists yet, but I wonder if there's something special about it. So I'm just gonna keep it there. Obviously, we have a perpendicular here and a perpendicular here, and not only that, they should meet at the center of this circle. So they should both pass through. I'll rename it O. I don't think I drew this one right. Oh, I drew MN. I don't want to draw MN. I want, let's see. I drew MN instead of MO. That's what happened. All right. Maybe it's also good to let EC intersect AD, because that would give us a cyclic quadrilateral. So I'm going to try that. Hopefully it'll be on the screen still. Yes. Whoops. I should mention that this is 2022. Okay. So we have HMON is cyclic. Can we say anything about point G? So let's see. Maybe I wonder if these are concurrent. I think they are. So I think we could redefine, one thing we could do, we could redefine G to be the intersection of this with CD, and then we could try to show those are each tangent. So we could call it G prime. I think that might be a better way to do it. So let G prime be the intersection of these with CD. Let's call it something different. Okay. We want to show BG prime is tangent to this circle, and then by the same logic, AG prime would be tangent to this one. So I think that's a good way to do it. And let me just make 100% sure that that's actually true, because I don't know if that is true. I think it is, though. So the tangent from B to BMP looks pretty true. All right. Okay. So what do we know? So HK is the polar. I don't know if we want to let AB and CD intersect at a point. But HK would be the polar of that point. I mean, so I think HK, G prime and this point are in harmonic conjugation. Since M and N are midpoints, we know that like BKC and AKD are similar, and M corresponds to N, so that gives us a lot of information. So in fact, I think ABMN might be cyclic, because oh no, that's not true necessarily. But yeah, so we want to show angle G prime BC is equal to angle PBM. Is that right? Sorry, BPM. Maybe they're similar triangles. So if I draw, is BPM similar to G prime BC? Let's see. So that's 98 degrees. And this, oops, sorry. I think they are. No, I don't think so. Very close, but they're not. Interesting. But we should have that this angle is 18.06. We should have that it's equal to this angle. Yes.
Can we try to do something like angle change or something to use that AC is tangent to ADQ?
AC is tangent to ADQ. Well,
also BD is tangent to CBP or whatever.
Yeah. So
because
yeah,
we have to somehow use that fact.
We do have to use that fact, yes.
Yeah.
So that could help. We also need to use that these three are collinear, because so let me check something. Oh, I almost thought those were cyclic, but I don't think so. So angle G prime BC We know it's tangent to, we know BD is tangent to this circle. So it's going to be DBC minus DBG prime, right?
But DBC is also, DBC is equal to DQA.
DBC is equal to DQA. Interesting. So that would be DQA minus DBG prime. So this is PM and it's QN.
Also, triangle DAQ is similar to DCB.
BCP.
DCB. DAQ, DCB.
Oh, DCB.
Yeah.
DAQ and BCB. That's interesting. And then DAB is similar to so you said DCB and DAQ are similar. Then does that mean that DAB and DBP are similar?
It means CAB and no, I think.
Oh, CAB and C. CAD and CBP. That's what it means, I think.
Yeah, exactly.
CAD and CBP.
Maybe we can, because DAQ and DCB are similar, the midpoint of DA would correspond to the midpoint of DC.
Okay. The mid. So yeah, we could try to use that fact. So yeah, maybe GG prime, maybe GG prime MN is cyclic.
No.
But or maybe GG prime AB is cyclic. Yeah, that looks true. So we could even define G prime that way if we wanted to. Yeah, let's see what works. I think you can use I think once you define G prime to be the intersection of HK, you can use harmonics, I think, to show that this is cyclic. Because if you let A, B, and C, D meet at a point, I think you can show that, like, yeah, I think you can use harmonics to show that this is cyclic right here. And then from there, maybe the angle chase is easier.
We can now find, for example, angle NQA.
NQA or MQA?
Which will be equal to NAG prime. NQA.
NQA.
Yes, is equal to NAG prime.
NAG prime. Okay, that's probably pretty helpful. So,
which is also equal to angle GBC by similarity, if I'm not wrong.
GBC. Yeah, that's going to be really helpful. Okay, so in the end, we want to show that G prime B is tangent to this circle. Is that right? So we want to show to BMP. Yeah, so we want to show angle G prime BC is equal to angle BPM. And what can we do with angle BPM? Well, we know it's BPC minus. Well, wait, we had similar triangles like you mentioned. So
Yes, BPM could be expressed as something with G. I think.
yeah. So let me write down what similar triangles were again. So BCB is similar to QAD, and ACD is similar to PBC. So we have both those similar triangles.
No,
And
angle BPM is equal to DAG, right?
BPM is DAG. I think you're right. Yes. So BPM is DAG. So we want to show that DAG equals G prime BC. It almost looks like these are parallel. So first, let me check that that's true. So DAG and G prime BC. Yes. So we want to show those are equal. Is AG parallel to HG prime? No.
It is enough to show that since G prime, G, A, and B are on the same circle, I think we can use that angle G prime AG is equal to G prime BG.
Okay. And so then we want to show angle CBG is DAG prime. Is that right? I think so.
So it's enough. Yeah, that's enough.
And 39.5. Oh yeah, they're both 30.5. So yeah, I don't even know if we really need point H, or if we could just define G prime and G this way. So we want to show that this angle is equal to this angle. So G prime AD. So let me try this. So BCD is similar to QAD. Wait, if G prime BC is okay, never mind.
Also, maybe at that angle equality, we can also use that angle CAD is equal to CBD.
CAD is CBD. Yes. So I think in the end we basically we're showing that this angle is equal to this angle. No.
Is equal to NQA, the other.
NQA.
Yeah, I think. Yes, exactly.
And that's the same. Okay, that's the same as saying, oh, but we know that by the tangent c, right? Because angle GAD but we're trying to prove it's tangent. So, but wait, maybe it's we know AC is tangent. So, yeah, I think.
It's also enough to show that CAG is equal to NQD. Or G prime AG is NQD, I think, if I'm not wrong.
CAG prime is NQD.
Yeah.
So yeah, they would both split it in the same ratio, basically. There's like one more step we're missing. We haven't used that ABG G prime as cyclic yet, right? So
I think by using that, we should be able to prove the.
Yeah. B prime BC. We want to show it's equal to.
Can we get rid of O and H and K? Just maybe we could easily see.
Yeah. So yeah, we can get rid of a lot here. We probably don't even need M and N, right? Well,
yeah, it depends, but okay, we can get rid of them also.
Right. Fact. Yeah, all we really need, we don't even need Q. Yeah, we don't need a lot of it because we just reduced it to something with G and G prime, right?
Yeah.
We don't need K. We don't even need K, I don't think, right?
No, we don't need K.
So really it's just oops. Let me do it this way. We want to show G prime BC is DAG. Or equivalently, we could show CBG is DAG prime. They're kind of both showing the same thing.
Yeah.
But yeah, I think it actually might help adding some of the stuff back in the figure. Let's see. So they're kind of like, maybe it's the law of sines, because like we want to show that these angles are equal, but then these Well, okay, they're not. I was thinking they'd be 180 minus each other, but they're not.
Yeah, but maybe we can also use that G is midpoint of CD using the lowest sign.
Okay. So we have sine this over CG prime is sine of this angle over BG prime, and then we have sine this over GD equals sine of this over AD. So yeah, I mean, maybe it is a lot of sines enough times. Let's see. So sine G prime BC over CG prime sine C over BG prime and sine of GAD over GD is equal to let's see, that would be sine of AGC over AB. And sine AGC is sine A BG prime. AD. And we want to show that those two are equal. So we want to show that CG prime is equal to GD over AB sine of ABG prime.
Maybe we can get the midpoints and the circles back.
Yeah.
The P and Q.
So yeah. Yeah, maybe I don't need H. H. Well, I'm not sure if it would be. Let me just keep the whole thing. Oh, we never used that OG is perpendicular to CD. That could be useful. Yeah. Let's see. So angle DAG we know kind of well. We just have this triangle and that's the median. Yeah, maybe we could do something with some medians. And then we want to show it's CBG prime. So yeah, I wonder if we can use harmonic quadrilaterals.
I think I found the way to use the cyclic.
Okay.
Because angle AGC is equal to QNA.
Yes.
But that will also be equal to G prime BP.
G prime BP. QNA is G prime BP?
Yes, by the cyclic. Yes.
Oh. So, sorry, QNA is G prime BP. I don't see it just yet. So QNA, you're saying is G prime BP?
Yes, because QNA is equal to AGC by the similarity.
Just AGC. Okay, so AGC. Whoops. Which wait, QNA is AGC? I don't think that's right. Let me check it one more time.
I don't know why.
I wonder if we can use harmonic quadrilaterals. So let's see. Basically, we just want to show that these two are equal. And you know HK and G prime are collinear. I think that means that, yeah, so the tangents at A and B would meet on HG prime. I think that's what that means. To this circle. Yeah, so I wanted to use medians and semedians. So this would be a semedian, and so if we take the midpoint of AB, but I should be able to do it a different way. So yeah, I
Can
think.
you also try the? Okay.
Oh, sorry. I was saying if we take the midpoint of AB, then I think we should also have it with point C and D. So I think that might make it easier. So if that's the midpoint of AB, and we label this point right here, then basically by the same logic, C, I, J, and D should be cyclic. So, and the reason why I think that might be helpful, it's hard to see, but because then we could use, if that's true, then the tangents at C and D should concur on this. And so G prime would be a semedian, and so JG would be a median. But yeah, that might make it more complicated. So I'm gonna actually, I'm not certain that would make it harder. But yeah, but what were you thinking?
I was thinking the angle that I said before, I calculated it wrong because QNA is equal to BGC.
Okay,
Not AGC. It was my mistake. I'm sorry.
it's all right. The QNA is AGC,
BGC,
BGC.
I think.
Let's see. Yes.
No, BGC is equal to G prime AB.
Okay.
Will this finish?
Let's see. So we have G prime AB.
Yes, we'll have that. G prime AB is equal to A and Q.
Is
But
equal A and Q.
yes, we want, what do we want? We want angle.
We want G prime BC equals GAD.
We want G prime A to be tangent to an AQ, right?
And NAQ. So yeah, we want G prime A to be tangent to it.
Yes. So we want angle G prime AD to be equal to G prime AD to be equal to angle AQN.
Yes.
But G prime AD is equal to BAD minus BAG prime.
BAD minus BAG prime. Okay.
Which is equal to BAD minus A and Q.
A and Q. BAD minus A and Q. Which is
Yes.
angle
Yes, I think we're
AQN.
done. Oh, nice. Because BAD is 180 minus QAD.
Okay, I think I've got this. So angle BAG prime, or sorry, angle G prime AD. Okay, so G prime AD is BAD minus BAG prime, which is BAD minus ANQ, which is angle
Which is
AQN.
Yes.
And that solves it. Okay. And we know that this is equal to this by because DC
Because of a
is
similar.
similar. And we know that this is equal to that by the cyclic quadrilateral. Okay, so we can delete a lot of stuff. At least hide a lot of stuff. So let's see. So we could just define G prime to be the intersection. I'll just keep that, but we don't need this. Okay, and we don't need this. Okay, so let me write this out. So BCD is similar to AQD by an angle chase. I might just leave it at that. Let me just think about that for a second. So BCD
is QAD.
So angle BCD is angle QAD, and then can we get one other angle in that to show they're similar?
I think I got it by the given tangency.
Okay. So angle BCD is QAD, and AQD
we can get angle CBD.
CBD.
Angle CBD is equal to CAD.
CBD is CAD. And then from there we use the tangent C.
Yes, we say it's equal to AQD.
Which is AQD. Okay. So, okay, so BCD is QAD. I'm just writing it down. All right, looks like we have another person joining. So BCD. Okay. Hey, Anurag, thanks for joining. So we have angle BCD is angle QAD. And hello. And then we have CBD is CAD is AQD. And that implies that triangles are similar. With G corresponding to N. Okay. So I'll say, so let me say let G be the midpoint of CD. And let ABG intersect CB at G prime. All right. So yeah, G is the midpoint of CD, and the circle, sorry, ABG should intersect that at G prime. And then first we have this. So that means that angle GNA is BGC. So I'll write that down. So QNA equals BGC which is BGG prime, which is BAG prime. Okay. So QNA is BGC, which is BGG prime, BAG prime. Okay, and then we can do it one more angle chase. So, okay, so we'll call this QNA. All right. So then we have angle G prime AD is. Dang, my Twitch just fell asleep. BAG prime, which is angle EAV minus angle QNA, which is angle AQN. That implies that BG prime, so if G prime AD is AQN, that implies that AG prime is tangent to AQN. QN, similarly, BG prime is tangent to BMP. And that solves the problem because that means that CD and the two tangents in the problem concur at G prime. All right. So yeah, this is a nice one. So yeah, just similar triangles, nothing fancy. So yeah, I mean, GeoGebra helped a lot again, of course. So here is the next problem on the short list. We have a triangle, and O is a circumcenter, and then we take any point on BC. Yeah, this one doesn't look that hard either. So O is the circumcenter. Then we take the line through D, perpendicular to BC, and we want to see where does it intersect AO, AC, and BC. Okay, so let's draw the whole ray here. And AO, AC, and BC. And I think there's like, I wonder if like the circumcircle of these three passes through like the midpoint of, I feel like I've seen something like this before, but we'll see. So yeah, let me draw the midpoint of arc BAC, because I think I've seen, I wonder if that's cyclic, but we'll see. Okay, so let me name these things right. So it intersects AO at W and AC at X and AB at Y. And then we draw, okay, so yeah, it does ask for the circumcircle of AXY. Let's see if it passes through G. No, not necessarily. I wonder if it's worth labeling the intersection of that circle though with ABC. So I'm gonna do that. I don't know why, I just feel like I've seen stuff like this before. So I'm gonna label this point. Prove that if, oh, it does ask for that. See, I didn't even read the question and I guessed that might be useful. And my Olympiad experience is coming into play. So prove that if W is not D and OW equals OD. Okay, so it's like a conditional statement. We need OW equals OD. I did not expect it would ask, it would want that. Okay, so we need OW equals OD. What's the best way? If I make this like a taller triangle, I think it might be a little easier to think about. So we want OW equals OD. Okay. There's probably a way to draw this figure exactly. For now, I'll just do it like that. And BZ is tangent to the circle AXY. I wonder if OD and Z are collinear in that case. So what does that mean? O, it almost looks like that's true. Let's see. I mean, that would mean that this, I think that would mean that this should be a right angle. I wonder if O lies on the perpendicular bisector of AZ. Sure, it looks like it. This is a very weird problem. What if I make it like a really tall triangle, let's say? So something like this. Now I want to move D around. Then it would be more like that. So I mean, basically, let's think about it a little differently. So
Or OD and Z collinear.
Are what collinear? OD and Z? Yeah, I think they might be. That's what I think.
If the
I haven't proven it, but I think that's the case.
condition holds.
Yeah. So if we let AO meet BC at point E, then if OW equals OD, since this is a right angle, then that would also equal OE. And so O would be the circumcenter of WDE. And so then we'd have BD equals EC. So yeah, we'd have a lot of symmetry. And then if that were true, then yeah, by symmetry, like OA equals OZ, like Z would be the reflection of A over the perpendicular bisector of BC. So is OA, can we show that OA's tangent? I think, because then if that's true, if we show that OA's tangent to the circle, then by symmetry we would have DZ as tangent. So to show that OA is tangent, is that just an angle chase? We'd want to show that OAC is 90 minus this. Yeah, so that would be too easy almost. I think this problem might be too easy, to be honest, unless I'm missing something. Because yeah, if you just, so let me type up what I'm thinking, and you guys can let me know if I'm missing something, but it looks to be not that hard, to be honest. Like first we let AO meet BC at E, that's the first step. And then we would have O, since OW equals OD, and this is a right angle, then that means that we'd have to have OW equals OD equals OE. So OD equals OE, and O's the circumcenter. So by symmetry, like everything has to be symmetric about the perpendicular bisector BC, right? So if we reflect segment AE over the perpendicular bisector, it's segment DZ. And so to show that DZ is tangent, we just have to show that EA is tangent, and that's just an angle chase.
But how do you know that D, O, and Z are collinear?
Oh, you're right. I kind of just, yeah. You're
If
right.
we prove that, then yeah, we are done.
Okay. Yeah, you're right.
What if we define Z to be that point, DO cap the circle, and then try to prove the cyclic?
Okay. So like this. I wonder if the circumcenter of this is the midpoint of BAC. So let me see if I still have that point. I think I erased it. But is this the circumcenter? No. Okay, so it's a little bit harder than that. Okay. So we want to show that cyclic. Let's see what the center is. That would be the center.
angle AYX is 19 minus B.
Yeah, AYX is 90 minus B. Maybe we could show AZX is that also. We know AZ is parallel to BC. That could be helpful.
So we need to show angle ZXF is equal to angle B.
ZXF is equal to angle B.
Yeah, it's
Yeah, and they're only slightly different because I didn't draw the figure exactly.
we can calculate angle AXY by 180 minus X.
So AXY is 90
Y
C,
X
right?
AY. Yeah, it's 90 minus C. But what about angle ZXC?
ZXD?
ZXC.
ZXC. Are AXY? Oh, I was thinking maybe they're similar, but they're not. ZXC. I wonder if there's some spiral similarity that we could use to show that this is cyclic, because if it is,
Can we find a, can we maybe find a cyclic quadrilateral that has ZX and C in it?
ZX and C. Okay. Ah, might
D.
pass through D.
Can you move A or something just to be sure? Or D, just.
Let's see. So if I move D, so yeah, I'd want to see. Yeah, I think it's true. We want OT equals OW, so let's see. If I move it around. Oh, I just drew it in a weird way, so it won't. But yeah, let me redefine. Think about how to do this. I mean, that would mean this is a right angle, right? One sec, I'll be right back. Sorry. All right, I'm back. Okay, so
As you mentioned spiral,
okay.
I think Z is some kind the Mikhail point of AXDB.
Ah, it's a good point. So then,
Yeah, so then we have the cyclic. If we prove, but no, they are not necessarily collinear because AXDB is not cyclic.
it's not cyclic, yeah.
But
So
if we prove DXZC is cyclic, we would also get the wanted cyclic. Yeah.
this would be cyclic, and oh, but we know that ZABC is cyclic. So we just need yeah, either ZXTC
Yeah.
or YZDB. One of those two. It seems like it shouldn't be hard to show why ZDB is cyclic, because Z is just a reflection of A over the perpendicular bisector. Like, oh yeah, if we show one, then we show the other actually, because this angle, we want to show it's equal to this angle, but that would be ABZ, which we know is ACZ. So yeah, either one is kind of showing the same thing. I kind of like, yeah, trying to show that this is a right angle here, CZX. So yeah, I'm going to hide that just for now. So we want to show CZX as a right angle. What if we did this? We let CZX be a right angle, and then we try to show that AZXY is cyclic.
Okay, but no, we also don't know that DO and Z are cyclic. DO and Z are collinear.
So we could define it that way. So given a point D, well, I'm wondering if we could redefine it somehow. So OW equals OD. We could define Z to be the intersection of DO with a circle. And then we could drop a perpendicular. So then this shouldn't be, oh, but then we don't know that it lies on AC, I guess. Yeah, something. Yeah, it would be a little tricky. So we could first define X. I'm thinking the best way to do it. We could define X like this and then show it lies on AC. So maybe first we could show this is cyclic, and then we could show AX and C are collinear. So this would be like X prime. It's a little bit complicated, but I think it might be okay. So like let X prime be this, and then angle AZX prime would be angle AZC minus 90. And I think it's easy to show that that's angle AYX prime. So then that would show that these are cyclic. And then once we show these are cyclic, maybe we could show AX prime and C are collinear. So to do that, we would want to show, we could try to show BAX prime as BAC.
Also, if Z is the intersection of both circles,
yeah. So
then we would get C, Z, X, and D as cyclic by angle chasing, I think.
yeah, so then this would be cyclic. We just have to show AX prime and C are collinear. And
yes.
that doesn't feel like it should be that hard. So yeah, I kind of like this strategy. I guess by Mikkel's theorem, well, no, we wouldn't be able to use that. But I mean, would we know that OA and OZ are tangent? Is that just oh, okay, I have an idea. So angle ZXC, ZX prime C is ZDC, which is ADB. And we want to show that's 180 minus AX prime Z. So basically we want to show ADB as AYZ.
Also, ZDC is equal to AEB.
ZDC is AEB. Yes. That's another way we could try to show it. We didn't even show, I don't think, that OA is tangent. Well, I guess we're kind of trying to show that both are tangent. But yeah, we have to show AX and C are collinear. It feels like it shouldn't be that hard, but it is. Okay, I think it's the same as showing. So I mean, we could try to show x prime y is cx prime d. Cx prime d is czd, and ax prime y is azy. So it's the same as showing these are isogonal. And maybe we can use the isogonal line lemma, because that would be the same as saying that ZB and let's see. It would be the same as saying, interesting. So ZX and ZB are like isogonal.
I also think that what if we define x the same as in the problem again? AC cap D.
Okay. We can.
Because I think I see a way to show that dxzc is cyclic.
If we define x as the intersection of AC with this.
Yes, because we will have that dzc is equal to BAE.
It's equal to EAB.
Yes, which is OAB.
Oh, yeah.
And
no, that's a good way to do it. Yeah. The OAB is the key. Yeah. Okay. So that would prove it's cyclic.
We also know that AXZY is cyclic, right?
Let's see. How do we define? So if we define Z as, so are we defining, if we define Z this way? Yeah, I guess it depends how we define Z. So, I
think we are done because I showed that if Z is defined on the problem as the problem, yes, I showed that dxzc is collinear. Dxzc is cyclic.
Yeah.
Because look at the angle YAZ is equal to YXZ.
Yeah.
Which is 180 minus ZXD. But YAZ is equal to ZCD.
ZCB. YAZ is, yes. So yeah.
No, that is also cyclic.
So YAZ is YBC is ZCB is ZXA. So then we know that has to be cyclic. Okay. So yeah, so it looks like we've solved it. So yeah, nice solution. So before I forget, it was we said CZD is EAB. So CZD is EAB, which is OAB, which is 90
minus ACB.
Which is 90 minus ACB, which is EXC. Okay.
But so, I think we also have, I don't see how to prove DZ is a tangent to AX.
Oh yeah. So yeah, then we know all that. So then how do we show its tangent?
I think angle chasing again.
Yeah. Because basically we'd want to show that this like angle OAZ is like 180 minus AXC. So we want to show OAZ is CXC, but CXC is CBZ. Yeah, and these two triangles are similar. So yeah.
Yeah, it's kind of true. And also we know that AZ is parallel to BC.
Yeah. So let me first define Z prime like this. So let Z prime be such that AZ prime CB is an isosceles trapezoid. So since OW equals OD, then by symmetry, D, O, and Z prime are collinear. So, I mean, I guess it's not that obvious, but it doesn't take that much work to show it. So we have V, O, and Z prime are collinear. So, and then okay, so then first we try to show this is cyclic. So we have C, Z prime D. EAB, which is angle OAB, which is 90 minus CB, which is C. And that means that CDXC prime is cyclic. And then we also want to show this is cyclic, but that's not an difficult angle chase either. So we have YAZ prime equals YBC, which is Z, which is ZCD, which is ZXY. Okay, so I'll just make them all Z prime. So angle YAZ prime equals angle YBC, which is angle ZCD, which is angle Z prime XY. That implies that AXYZ prime is cyclic, which means that Z prime equals C. And then so once we've shown that, we just need to show that OA is tangent, right? And that's an easy angle chase. So angle OAZ, so angle OAZ is OED, which is ODE. So actually it's probably, we could just probably say angle OAZ is angle EAZ, which is, oh yeah, there's more than one way to write it. So angle OAZ, I'll write it like this, OZA, which is angle is angle ZDC, which is ZXC. C. And that implies that implies that OA is tangent to the circle. Or I'll say DA is tangent to AXY. Implies DZ is tangent to AXY by symmetry. All right. Okay. So yeah. So a lot of these problems, let's see, this one was mostly angle chasing, this one was angle chasing and similar triangles. Yeah, so nothing super sophisticated yet. This one, let me skip this one for just a sec. This one looked kind of interesting. So it's a short problem